estimate the errors in measurement? Can we characterize the errors? And can we really take care of the errors in our measure data, right? Can we correct our data considering the errors that we expect? So if you look at, if let's say you are measuring temperature of a surface, how do you define error? So typically, error is defined as the difference between the measured value and the true value. Okay, so you define error E as the difference between the measured value, let's call it X subscript M, and the true value. Okay, X subscript T. Okay, so let's say you have a surface and which is at some temperature, and you want to know the temperature of this surface, and you do some measurement, right? You put in a thermocouple and you have some temperature measurement, right? You get some value as the measured value. But how do you know that how much is the error? Because you would not know the true value, right? If you knew the true value, there is no need of the measurement, right? So essentially, the true value is a hypothetical concept, right? In most cases, the true value is a hypothetical concept because the true value is never known. And if it is known, then there is no need of any measurement. So you can sort of qualitatively say that your data will be accurate if the measured value is close to the true value. Okay, and the closeness of the measured value to the true value sort of represents accuracy. Okay, so since the concept of true value is hypothetical, the concept of accuracy is qualitative, right? So most cases, you do not know the true value. It is not known unless, there are only few examples. Let's say, you want to do some experiment to evaluate the value of acceleration due to gravity, which you already know, right? 9.81 meter per second square. And let's say, in high school, you would have done this simple pendulum experiment where you measure the time period and you know the length of the string. And from there, you actually predict or measure the value of G, right? So in that case, you actually know what is the true value of G because this is known from theory, and that is a 9.81 per meter square. So you can really, in this case, you can say, okay, my error is this much. But most cases, you do not know, like temperature of the surface, you do not know what is the true value. You only measure, and and that's all. You don't have a true value. So we will come to another parameter, which is known as uncertainty. So a while from now. So, but for now, you sort of should understand that error is in the measurement is a hypothetical concept. Okay. Now, if you take, let's say same example, you are trying to measure temperature of the surface using a thermocouple, and you take, let's say, 100 data points, right? Let's say this is the reading number. You took 100 data points, and the y-axis you have the measured value, the temperature that you measured. So if you basically, plot the first reading can be here, second reading can be there. You can have third reading can be there. You can have all kind of fluctuations, that is possible, right? You are never going to get a single value, right? And when you take sort of the mean of these values, so you get something like that. Okay, and around the mean value you have the scatter, right? Let's say hypothetically you know that, okay, the true value is here, this is the true value, and if you take the difference between the mean and the true value, this is known as systematic error. Systematic error. And the scatterness of this data gives rise to what is called random error. Okay, so errors, although they are hypothetical, they are qualitative, can be divided into two types. One is systematic error, and the other one is random error. Okay, systematic error is also known as bias error, and random error is known as precision error. Okay, so now I want to show that in terms of data. So if let's say you have the y-axis representing frequency and x-axis is representing your data. So if you do any kind of measurement, if the measurement is done properly, you typically get this kind of bell-shaped curve, right? Which is the Gaussian curve. And any measurement which is carefully done, your data must follow this kind of curve. Okay. So you have the central value, and this central value is known as mean. Okay. Most of your data should be cluttering around the mean. Now let's say you know the true value. Let's say the true value is here, right? X true is here. And let's talk about a particular measurement. Okay, let's say the particular measurement is here. We call it XM, right? So the difference between the mean and the true value is known as the bias error or systematic error. Bias error or systematic error. And the deviation of that particular data point from the mean is known as the precision error or random error. Okay, and this particular data from the true value gives you the total error. Okay, so basically errors have systematic or bias error and random or precision error. So together systematic error and random error will give you total error in the data. So in this particular case, you can see the way I have drawn, the bias error seems to be higher than the precision error, but not necessarily always. Okay, there are cases where precision error can also exceed a bias error and vice versa. Okay, so what is actually systematic or bias error? Okay, as you can see from this graph, it is basically the offset between the mean value and the true value of that particular data. So let's say if you measure temperature, the difference between the mean temperature and the true temperature, right? So the systematic or bias error can appear, let's say One reason is if you have a faulty or improperly calibrated instrument, right? So this bias error can happen because of faulty or improperly calibrated, improperly calibrated instrument. Okay, let's say you have a thermometer which consistently is measuring 1 degree centigrade higher or 1 degree centigrade lower. So you always have that error inbuilt. So since you know that error quite well, you can actually correct. Okay, so systematic error can be corrected. Okay, but random error or precision error can appear. Basically, it appears in the data because you are doing repeated measurements, right? If you measure only once, you have only systematic error. But if you repeat 100 times, your data is going to vary, and that variation of the data points from each other gives rise to the scatterness in the data, and the scatterness gives you the random error. Okay. Now, what is the source of this random error or precision error? There are different sources of random error or precision error. One possible source is, let's say you are measuring, there are some external disturbance. Okay, let's say you are measuring temperature, suddenly somebody opens the door, right? And you have, let's say, hot air comes in, right? Or somebody's working somewhere in the building and there is vibration, right, which is affecting your measurement. So all these practical scenarios, real life scenarios, the disturbances are plenty, and these can really affect your measurement, and that consequence is the in terms of the random error. Okay, so this is typically because of external disturbances which are inevitable during measurement. How much care you take, but there is always going to be some disturbance, and you cannot correct for random error because they occur randomly and you have no control over that. Hence, you cannot correct, but you can characterize them using statistical analysis. So random errors are characterized by statistical analysis. Okay. So before we go further, I wanted to differentiate between accuracy and precision.
Sir, 1 minute, sir.
Yeah.
Sir, you told this true error is like a hypothetical concept like that.
True value is hypothetical in a
If
typical measurement.
if you don't know the true value, how will you correlate this parameters like systematic errors?
Yes, so we are basically learning the concept. Okay, but in reality, you would only know the systematic error, because let's say, as I said, right, you measure your this is data, right? This is data, and let's say you have used another tool to measure temperature. Let's say you have another method. Let's say you have used thermocouple or IR thermometer to measure the temperature of the surface, and they agreed really well. Okay, let's say they are measuring the surface temperature at that condition, let's say 55 degrees centigrade. Okay, and let's say you put in a thermometer and you are measuring 53 degrees centigrade. Of course, always, it is never 55 and 53. Let's say in 55, it will be 55 plus minus something. Let's say here 53 plus minus something. So that 2 degree cannot come from random error. Random errors would have, let's say, some 0.5 degree, 0.1 degree, 0.3 degree, and so on. So the bulk difference you can attribute to what is called the bias error. Okay, so that means you say that my thermometer is faulty, or I have not calibrated it properly. It consistently showing 2 degree lower than the actual temperature, right? So you can correct for it. But the problem, the most tricky thing is the precision error, because you measure once, you measure twice, you measure thrice, you measure 100 times, you get all different values. Okay, you get 50.1, 50.2, 50.3, all kinds of numbers you get, right? So my point is, if you have any bulk difference, it can be attributed to the systematic error or bias error. So you can really correct for it, but you cannot correct the random error or precision error, which is really taken care of through statistical analysis. So you define some standard deviation, and there are n number of different ways, and you define, what is the accuracy that you need, okay, what kind of sigma limit you need. So depending on that, you basically adjust your numbers. Okay. So, but that is something we'll go through, I mean, in this class, right? So that is the course about. We will talk about, when we do some measurement, what is our best estimate, right? You measure the temperature of a surface, you do not know what is the true value. But all you can do is, if you do measurement, you can define your limit, okay, within, let's say, plus minus sigma, plus minus 2 sigma, and plus minus 3 sigma. You say that you are 99.9% sure that your actual temperature of the surface will fall in this range, okay? Or if you say within plus minus 3 sigma, you're 95% sure that your actual temperature of the surface will fall in this range, right? So this kind of precision or random error we will be handling through statistical analysis. So we'll deal with this later. But for now, as I said, any bulk difference would be attributed to systematic error, and any small changes which are very difficult to control is attributed to the precision or random error. Does that answer your question? Hello?
Yes, sir.
Okay. So let us talk about accuracy and precision through these examples. So let's say we have these targets. We consider 3 cases. Okay. So let's say, I mean, these 3 are identical, although I have not drawn identical. So you have some industrial robots which are supposed to carry some object and place them right at the crosshair. Okay. And in different situations, you get different kind of distribution. In one situation, you get these objects placed something like this. Okay. In another case, the robot basically places the object something like that. And in another case, the robot places the objects something like that, right? So in terms of accuracy and precision, let's start with this. So what is this case?
It's precise, sir.
It is highly precise, right? So it is highly precise, but the accuracy is low, right? High precision and low accuracy. This is a case where low precision and low accuracy. And this is a case where you have high precision as well as
high accuracy.
high accuracy. Okay. So basically, you can now relate to what we studied just now in terms of the bias and the precision. You see that, you know, when the data points are scattered from each other and also very different from that of the true value, you can say that, you know, it is low precision and low accuracy. But when the data points are very close to each other, but they are different, quite different than the true value, then you can say it is highly precise, but the accuracy is low. But when the data points are all close to each other and also close to the target, you say that it is high precision and high accuracy. So this should be straightforward to understand, right? So before we move further, I would like to define a few parameters. Okay, so we would talk about
Sir,
few definitions.
one question I want to ask,
Yeah.
if you allow, please.
Yeah.
Sir, basically that the Gaussian curve that you have shown na, in the just before this.
Yeah.
So if I want to plot these three situation on that plot.
Yes.
So in the first case, like if I've understood correctly, that means the random error will be very high, right, sir, compared to
Yes.
bias error.
So basically, you say that this bias error and this precision error both will be very high. Okay.
Okay, sir.
This
Okay.
Gaussian curve will be very wide, and the mean will be very different from the true value. Okay. It can be
Okay.
something like this, right? And
Right.
the second case, it is highly precise, right? That means it may be something like that. It is precise, but it is very far from the true value. And the
Right,
third
sir.
one would come something like this. Okay. It is precise.
Thank you.
Also, it is accurate.
Thank you so much, sir. Thank you so much.
Sir, can I just ask one question?
Yeah.
In that Gaussian curve,
Yeah.
is it necessary that the bias is always on the LH side of the mean, or
No. I think see the true value can lie actually anywhere. In fact, the true value can come somewhere here, right? So if the true value is here, you can see that the precision error here is very small, right, compared to the bias error, right? Or the true value can even lie here. You can see that the bias error is very small compared to the precision error. So it can actually lie anywhere. Okay.
yes,
Not
sir, I
necessary.
understood. I just wanted to clarify. Yeah,
Yeah.
thanks.
Sir, I have one question with respect
Yeah.
to the same Gaussian curve.
Okay.
So we made a case of we made a discussion about how this total error is calculated, right? Like biased error and precision error is combined to get the total error.
Yeah.
We also discussed that sometimes the precision error can overshoot the actual true value or be a bit of, due to the disturbances. So in that case, can we still define it as a combination or a mathematical formula of bias and precision together, or is it going to be subjective?
Yeah. So when we add them, we have to worry about the sign also, right? Because if the total error happens to be less than the bias error, then basically, you know, your precision error is going to be negative, right? So you have to worry about the sign of the error also, not just the magnitude.
Okay, thank you.
Yeah. Okay. So as I said, we will go over a few definitions. The first, I mean, these definitions will help us throughout the statistical analysis of experimental data. So it's important to understand these definitions. So the first definition we talk about is range and full scale output. Okay. So typically range refers to the input to the measurement system. For example, if you are trying to measure the deflection of a spring, as you increase this load, okay, let's say some load, and you are basically trying to know the deflection. So then here the range becomes basically the how much weight you can really, the spring can carry, let's say from 0.1 kg to 10 kg, right? So this input basically defines the range, right? The operating range. In case of thermocouple, what is the temperature range of the surface that you are interested to measure, right? In case of, let's say, flow through a tube, what is the inlet flow rate range, right? So this is basically the input, and the operating range you define as x max minus x min, and where x is basically the input, right? So similarly, the full scale output of course it refers to the output. Okay, let's say this you refer as Ri. I is basically stands for input, R is range. Similarly, full scale output is the range of the output, and this can be the Y max minus Y min. Okay, so full scale output is, in this case, let's say the deflection or the elongation of the spring, and in case of a thermocouple, let's say it is the output, the EMF, the output voltage that you get from the thermocouple circuit. So, and in case of a flow through tube, that is the pressure drop, right? You have varying flow rate, which is the input, and your output is the pressure drop across the tube. The second thing that we want to define is relative accuracy. What is relative accuracy? Relative accuracy is defined as the ratio of the difference between the measured value and the true value, because measured value minus true value gives you a representation of error, which qualitatively represents accuracy, divided by some reference value into 100. So relative accuracy, A subscript R, is defined as the modulus of E minus a reference value into 100, and this E is basically Y measured minus Y true. And this reference value can be anything, right? Because this is just used for normalization. It can be, for example, Y max, the maximum output that on the scale. And by taking the ratio and multiplying with 100, you get the relative accuracy. Then you can define resolution. Resolution is basically, as you know, is the smallest increment in the measured value that you can differentiate, right? And so typically, let's say you are trying to measure temperature. Is your instrument, good enough to differentiate between 1 degree and 2 degree, or it just measures 1 degree, 5 degree, 10 degree, and so on, right? So this resolution can be defined as delta x divided by x max minus x mean into 100. So what is the smallest change that you can really measure, and that with respect to the full scale, with respect to the operating range into 100. Okay, so the fourth one that we define is called repeatability. Okay, so let's say you have some input and you have some output. You have input, you have output, and for a particular input, you do, let's say, 10 measurements, right? And your data is going to vary within a range where you define your standard deviation and mean, and you change the input, you may get some other mean value, and of course you have a standard deviation. Or some other input, you may have some other mean and some other standard deviation, right? So for a given input, right, this variation in the output basically signifies repeatability. Okay, so the repeatability is expressed in terms of UR max, which is, and this variation is indicated by a parameter called Sx, which is the standard deviation. We'll talk about standard deviation later, but for now, you just qualitatively take it from me that it represents a scatter in the data. So the repeatability is mathematically defined as twice of Sx, the standard deviation, divided by the full scale output. Okay, basically this is y max minus y mean into 100. Okay, next we can talk about reproducibility.
Sorry to interrupt, sir. So repeatability is always percentage only, correct?
Sorry?
Repeatability is always in percentage, right?
Yeah, I mean, in fact, all these other things that I have defined here, if you look at, even this is relative accuracy is expressed in percentages, and so also resolution. But repeatability is also expressed in terms of percentage, as you can see here. Okay, so reproducibility, there is no mathematical formula as such, but how do you differentiate reproducibility from repeatability? How repeatability and reproducibility are different?
If the given input again and again, if the output is same, that means the instrument is reproducible in that way. Like for same input, if I'm giving to the measurement instrument, and it is giving me same output, then the.
But I thought that, I mean, I am talking about repeatability here. I'm giving same input and I am getting different output here. And I'm calling this as repeatability. So how reproducibility is different then?
Sir, I have an example.
Okay.
So we use the term reproducibility in our work a lot. So like if we have a brake system and it does a certain it produces a certain output under certain other conditions, we can recreate the same conditions on a different ECU and obtain the same output. So we are
Okay, I think
reproducing-
yeah, I got your point. I think you made a good point. You said that at a different condition, right? So let me talk in terms of that. Typically, in statistics, repeatability refers to the variation that you get in the data when the experiment is done by the same person using the same instrument under the same condition. Okay. And it is basically some statistical measure because you repeat 100 times and you say that, okay, my repeatability is good or my repeatability is bad because it is expressed in terms of percentage. If the standard deviation is very low, and then my repeatability is very good. Okay. But reproducibility is a more qualitative term. Reproducibility is basically based on multiple tests performed in, let's say, different environments, in different laboratories or different stations on a single unit or a model of that instrument, right? And you are basically talking about the degree of agreement between the results of the experiments conducted by different individuals at different locations and with different instruments. Okay, so meaning, let's say you have some calibration curve, temperature versus power heat input. Okay, and you get some calibration curve. For each data, you say that, okay, my thing is repeatable. But if you do the same experiment yourself on the same day and you are doing, again, that is not really reproducibility. Reproducibility is that somebody else has to really do that, maybe at the same condition, or you have to do it at a different location, or you have to do the same using a different instrument. Okay, so either any of these or all of these have to be satisfied to call it reproducibility. Okay.
Sir, I have a question here.
Yeah.
I agree with you on the repeatability, like on the, okay, if the same person measures the value, like, and he get a two different value, that is the check for the repeatability.
Yeah.
And the reproducibility is if two different person does the measurement or like at different conditions, that we can call it as a reproducibility.
Yeah.
But one point I want to get clarified is like the person needs to use the same instrument, right? Like he cannot use the different instrument, right?
So my point is, let's say, so we are talking about three different things here. The person who is doing, the place where it is being done, third is the instrument that is being used. Okay. So I am saying that at least one of these have to be changed for you to say that my results are reproducible. Okay. So instrument, let me give you an example. Let's say, going to this simple example of the spring mass system. Let's say you have developed a new material and you want to characterize, right? And you want to apply load and you want to know the elongation. And so let's say you have used this, let's say a linear variable transducer for measuring the elongation, right? And you are applying load and your LV dt is measuring the elongation. And you have some characteristics for that material. Okay, so this is the basically the load versus strain or elongation curve. Now, if you do the experiment in the same lab at the same location, but you use some other method, like let's say you use some kind of optical technique, right? You say that I was able to reproduce the results that I got, for this, for characterizing this spring. Okay, so the point is statistically, I mean, this is the convention that at least the individual has to be different, or the location has to be different, the conditions have to be different, or the instrument that you use or the method that you use have to be different. But if you use the same instrument, of course, you have to try out in a different condition, or somebody else has to really reproduce your results. Okay, so
Okay, sir.
basically 3 things, as I said: the individual doing the test, the location or the condition for the test, and the instrument that is being used. Okay. Then there is something called hysteresis. Hysteresis is like, let's say you are increasing the input and your output is changing. Let's say something like that, right? And then you reach the maximum input condition, and then you try to reduce. So ideally you expect that, okay, it will walk the same path backward, but many times it doesn't follow exactly the same path, right? It takes a slightly different path. So this is the upscale. That means you are increasing the input, and this is downscale. Okay. So for a given input now, you have basically 2 different outputs. Okay. So this difference is known as hysteresis. So how do you characterize hysteresis then? Because hysteresis is different here and hysteresis is different here. So typically the hysteresis is the difference of y upscale minus y downscale, or vice versa, because you can always take a modulus to make it positive. So you again express in terms of percentage hysteresis, so which is UH max, basically the maximum value of hysteresis wherever you get during the upscale and downscale, divided by the full scale output, which is Y max minus Y min into 100. Okay. Then we talk about linearity error. Linearity. So you have again input and output, and let's say you did some test and you got the data points, something like that, right? And if you join the curve, it goes something like that. But if you draw a linear curve, let's say you get something like that. So you can see that this is the actual data, and this is the linear fit. Okay. So linearity error at any point, right? So if you say at UH at a particular X is going to be Y at that X minus Y on the linear curve at that x. Like, for example, if this is the x that we are talking about, this is basically yx, and this is y linear x. Because this is where the vertical line is crossing the linearity curve. So again, you also express this in terms of percentage. So you say U linear is basically UL max, wherever the maximum deviation is, divided by the full scale output, Y max minus Y min into 100, right? So if all the points lie on the linear fit, that means the linearity error is 0, right? So data is perfectly linear. Okay. Then we can talk about sensitivity. What is sensitivity? Sensitivity, as you know, is basically, it represents the slope of the output input curve, right? How fast the output is changing with respect to a given change in the input. So you have input and output, and let's say this is a nominal curve, and if you have a characteristic of something like that, then sensitivity is less, and if you have the characteristic of something like that, the sensitivity is higher, right? So it is basically the slope of this curve. So you define sensitivity as the change in the output divided by the change in the input. Okay. And if you want to express in terms of percentage, so let's say this is the maximum sensitivity your data is giving. Let's say this is the minimum sensitivity the data is giving. Let's say this variation is some delta. So, and let's say this is your Y nominal. Then you can define your sensitivity error as delta divided by Y nominal into 100. Okay, so your data may be lying something like this, right? Okay, and you have a linear fit. So from the maximum to the minimum, let's say this curve joins the minimum value of the data sets. This is the maximum value of the data set. So you get delta, and wherever it crosses, that is basically the linear curve, that is the Y nominal into 100 will give you the sensitivity error.
Sir, I have a clarification to ask on
Yeah.
this. So you told, sir, this is the lower dotted line is basically the line joining the center and the minimum data point, right, sir?
Yes.
Like we have 100 measurement points, suppose.
Yeah. So maybe
out
let's
of-
say if you have a minimum here, so this will give you the minimum value of the line.
Single point, which is the minimum one.
Yeah,
right,
yeah,
sir?
you can get, yes, because the
Okay.
I mean there is a range, right? There may be
Right, sir.
maximum somewhere here, so that is the range. Okay. So we talk about threshold and drift. Input, output. So this is the nominal curve typically you expect. For some time, you may have the characteristics which looks like this. Sometimes the characteristics which looks like this. So in that case, you can define threshold and drift. Okay. So you can see that, let's say you have an instrument and you are measuring again, let's say temperature, and you change the heat input, but you see that the thermocouple is not responding. Okay, you started at 25 degree at, let's say, some input of 10 watt, you went to 10.1 watt, 10.5 watt. There is no change in the thermocouple, right? There is no change in the output. So that means your input is changing, your power that you are supplying is changing, but there is no change in the output. There is no change in the temperature, right? Up to a critical value of input. And beyond, if you go to, let's say, 11 watt, you started seeing that, okay, it is increasing, right? You get some different EMF in the thermocouple circuit. So basically, up to a critical input, your output is 0, right? And that critical value is called threshold. So every instrument will have some threshold, and if you have some input below that, you will not get any output. Okay. Similarly, if your instrument is faulty or you use instrument regularly over time, you may see that when you have 0 input, you are still seeing some output. Okay, you have no input, there is no excitation, but you see that your data, I mean, it is showing up, the output is showing up, right? And that is known as drift. Okay, when you get any output, when the input is still 0 and you expect the output should be 0, but you get a non-zero output, that is known as drift. Both drift and threshold are basically errors that the instrument brings to the measurement. So we need to account for them. Okay. So you have all these things that we define, right? Threshold, drift, sensitivity. Then we talked about linearity, hysteresis, repeatability. They all, when you buy a new instrument, their errors associated with all these definitions would be mentioned. Okay, let's say you buy a pressure sensor, it will have the input range of pressure that it can handle. Okay, so that is the first thing that we define. It will tell that, okay, you can measure between 0 Pascal to 1000 Pascal. It will tell you what output you expect. Let's say it is giving you some voltage. It will give you that, okay, corresponding to 0 Pascal, you should get a 0 voltage. Corresponding to 1000 Pascal, you should get, let's say, 20 volt, right? So the operating range and full scale output will be given in the instrument data set. Along with that, all these, resolution error, the linearity error, hysteresis error, sensitivity error, 0 drift, everything will be mentioned in the data set. Typically for an instrument, they should provide all this information so that knowing all these errors, you can say that, okay, if I do some measurement, what is the error associated with the instrument? Okay, so let's say all these individual errors you know. Okay, let's say you have the error due to linearity, error due to sensitivity, error due to drift. Okay, all these errors you have. Okay, in general, you call it, let's say, U1, U2, U3 up to UM. So you can find the instrument error, or rather you say instrument uncertainty. Now I have brought in another definition. Instrument uncertainty is basically U1 square plus U2 square plus U3 square up to UM square root. So this is the uncertainty that is coming because of the instrument. Okay. So here I can use either error or uncertainty interchangeably for an instrument, that is fine. But error and uncertainty are not the same. Okay. Error and uncertainty are not the same. So we need to understand that. Okay. So uncertainty is basically a numerical estimate of the possible range of errors in a measurement. When you do some measurement, if the error is only coming from the instrument, then you say that, okay, your uncertainty is same as the instrument error, because already, for the instrument, your manufacturer of the instrument has given all the errors. So you say that instrument uncertainty is equal to instrument error. But when you use that instrument to measure something, in addition to the inherent errors coming from these sources, the linearity, sensitivity, drift, repeatability, the measurement process itself also brings in several aspects, which brings in together, all these aspects bring in what is called uncertainty in the measurement. Okay. So that is why when we said that in any measurement, error is not known exactly. Okay, because the true value is not known exactly. But uncertainty is basically encompassing all the kinds of errors that can happen, right? Because of the instrument, which are all these linearity, sensitivity, drift, and all that, but also the external effects, right? What are the external effects? What method that you are using, what kind of system that you are using, where you are measuring, what are the external effects? Is there any vibration? Is there any change in the environment? So all these effects come in, and together they are all combined into uncertainty. Okay. So in one sentence, you would differentiate error and uncertainty. So basically, uncertainty, your error, is the property of an instrument. Okay. You can say that my instrument brings in this much error. But uncertainty is the property of the test results. Okay. So in a way, so this is the property of the test results, right? And this is the property of the instrument. Okay. And this uncertainty basically can include both the errors in the instrument and the external effect. Okay. Whereas this error in the instrument is sort of systematic, because your manufacturer has given all these, so you know what is the error. This external effect bring in the random uncertainty. So this bring in random uncertainty, whereas this instrument brings in systematic uncertainty. So when you measure temperature or when you measure pressure, you don't talk about what is the error in my measurement. You say that what is uncertainty of my measurement. Okay, and that uncertainty includes both the errors from the instrument and the external effects. Okay, so let us stop here. If you have any question, let us discuss.
Yeah, hello, sir.
Yeah.
Yeah, my question is that for a primary quantities, we have different units, right, sir?
Yeah.
So, in ideal cases, all these definitions should not vary, but they could vary in reality, right, sir?
I didn't get your question. Can you say that again?
So primary quantities such as temperature, we have two units.
Yes.
That is being used in day-to-day life, say the Celsius and the Kelvin.
Mm-hmm.
So these, in ideal cases, the value should not change of all the definitions what you have learned now, but there might be chances of variation in those units, right, sir?
Variation in the units meaning?
Variation in the all the definitions what you have used, what we have discussed, right? If we put on the measurement values in two different units, that is in Celsius and Kelvin.
Okay, I got your point. Okay,
Yeah.
so that is coming under the uncertainty, because the analysis that comes under analysis. Okay, so
Okay.
the method that you use to analyze would also influence your final data. Okay.
Okay.
So when we will talk about something called propagation of uncertainty, the round of error. Okay. So if you round off something, and if it is, let's say, squared, right, it will amplify differently. You may round off in Celsius, there will be some slight variation than if you do in Kelvin or Fahrenheit. So these round-offs would propagate into a difference in the final quantity that you'd get. Okay, so we'll talk about that. There is something that we will discuss, which is called propagation of uncertainty. So yeah, this is relevant. It's a good point, actually.
Okay.
Yeah, but that is coming under, that is included in the uncertainty. Yes.
Okay. Thank you, sir.
So one doubt.
Yeah.
Can you move back to the hysteresis slide? Yes, sir.
Okay, next one. Yeah.
So here, like how this y upscale and that y max, how it is differed? Like how do we calculate that?
So basically, I mean, you are increasing input and you get output. So you get a curve, right?
Yes.
And you increase your input up till some maximum, right? X max. And then you reduce, right? So these are actually, this curve is basically representing data sets, data points, right? You have increasing X and then decreasing X. So once you have these curves, so your upscale is when you increased the input from 0 to some maximum, and the downscale is when you came from the maximum to 0. Okay, and when you have these curves for a given input, you are basically having two outputs, right? So you know the point on upscale and you know the point on downscale. So if you take the difference, that gives you hysteresis. But for some input, you will see that the hysteresis is maximum, right? Maybe somewhere here for this particular curve. It may not, it is not maximum here, or it's not maximum there. It is maximum somewhere here in the middle. So that maximum, when you divide with the full scale output 100, that is the way you can define hysteresis.
Okay.
Okay, so if no question, thank you very much, and we'll meet again next week, I guess.
Yeah, sir, next week.
Okay, so have a good week, and we'll meet on Monday. Thank you.
Thank you, sir. Thank you so much.
Thank you,
sir.
sir.
Thanks a lot, sir.
Thank you, sir. Thank you,
Thank you,
and
sir.
same to you, sir.
Thank you, Professor, sir.